So our first speaker is Deepak Vasisht. Deepak is assistant professor in computer science at the University of Illinois at Urbana-Champaign. His research focuses on mobile computing and wireless networking, specializing in how next generation systems like satellite networks, 5G, 6G, N-body networks, and others can solve human-critical problems in different applications area like healthcare, smart homes, and agriculture. Deepak research on Internet of Things systems for agriculture like the Project FarmBeats, Microsoft Azure FarmBeats, has been deployed across farms in the United States, India, and Africa. His work has been featured in The Economist, IEEE Spectrum, BBC, MIT News, World Economic Forums, Daily Mail, and CBC. Deepak received his Bachelor Tech from IIT Delhi and his PhD from MIT. And at IIT Delhi, he was awarded the President Gold Medal. And in 2021, IIT Delhi named as a graduate of the last decade. His PhD dissertation received the ACM SIGCOMM Doctoral Dissertation Award in 2019, and his reception of the Microsoft Research Ph.D. Fellowship and an ACM SIGCOMM Best Paper Award. So Deepak, the floor is yours.
Hey, thank you so much. Thanks for the nice introduction, Mohammed. Hi, everyone. So I'm going to be talking about near real-time insights from Earth observation satellites. And this is a work that's been largely done by a lot of my PhD students at the University of Illinois. And I'll actually specifically name them when we come to the individual works. So I want to start by showing you some pictures that were taken by satellites over the last year and how important these pictures have been. So this is a picture from Ukraine before and after the war. At different locations, you can see like the damage that's been caused by the Russia-Ukraine war clearly through these pictures. This is an image of a forest fire in California in the last year, taken by a Planet satellite. And this is an image taken by a Maxar satellite of the Tonga volcanic eruption. You can see that the coast is kind of barren, and that is largely because of the volcano. And all these pictures have been taken by satellites launched over the last 5 years or so. And as you can see, there's a lot of interest in launching new satellites and deploying them in space over the last decade. This number continues to keep growing up. This number has already gone up by 5 to 10 times, and it's going to increase by another a similar factor over the next 10 years. And this is largely because of two reasons. One is because of the low cost of designing CubeSats or small satellites that can pack pretty much off-the-shelf components and launch them in space. And also through like new rideshare agreements where a lot of these small satellites can be packed on a single rocket and deployed. And one way to think of them is like Uber for satellites or Uber Pool for satellites, where multiple satellites pool together. So the cost of launching each one of them goes down significantly. And these satellites are typically used for two main purposes. One of them is communication, that is providing global connectivity throughout the Earth. So this would be companies like Starlink or OneWeb, which you'll hear about today in the second talk. And the other purpose is Earth observation, which is essentially like having a camera in the sky. So it takes images of the Earth and send them to ground stations on the Earth for reception and for analysis. So today, about like 1/4 to 1/3 of LEO satellites are meant for Earth observation. And that's going to be the focus of this talk. In the next talk, you'll hear more about internet connectivity through LEO satellites. And a lot of you are familiar with this, but just to give you some context, the way these satellites operate are in low Earth orbits. And what low Earth orbits mean is that they're about 500 to 600 kilometers above the surface of the Earth. And they have a very short orbital period. So compared to other satellites that you've heard about, say like geostationary satellites or MEO satellites, this orbit period is not like several hours or 1 day, but much smaller, around like 90 minutes. And a lot of these Earth observation satellites operate in polar orbits. And what it means is that the satellite keeps going around the poles, And given that the orbit period is not 24 hours, it's just like 90 minutes, you would see that the Earth rotates under it. And every time the satellite goes around, it will scan a different part of the Earth. So imagine I am in like University of Illinois, Urbana Champaign. I have one satellite in space, and I want to get one image of this university. So if I get one image today, the next time the satellite will be over me to take that picture would be about 6 to 12 days, depending on like different parameters. So clearly, to get more and more frequency of images, I would deploy like larger constellations of like tens to hundreds of these satellites so that I can get several images per day, and or like actually even one image per hour at the extreme. Okay, so these satellites have several nice characteristics. So for example, because of their low orbits, they can get high resolution. So it's kind of obvious. If you put a camera close to your object, you will get high resolution. As you deploy larger and larger constellations, you get frequent revisits. So you get multiple images of the same location every day. And the hardware continues to get better. So you can pack more and more capabilities into these satellites so that you can even get like multispectral imagery that does not just cover like RGB, but also radio frequency signals. Okay, so the question that I'm going to address today is this question of latency. So remember, I started by saying that, hey, we want to deliver near real-time insights from this data. So how long does it take today for an image to go from a satellite to a consumer? And the answer is that it can take actually hours to days. And that's okay for some applications, but for a lot of the applications like forest fires, floods, even like war zones, all of this information, you want to get it as soon as possible and relay it to whoever the end user is as fast as possible. So our goal is actually to reduce this time to insight from hours to days to few minutes. Of course, we'll not get there in this talk, but we'll talk about some reasons why this delay exists and what can we do to actually reduce that delay. Okay. So the key challenge here is downloading this data from satellites, and there are multiple reasons for this challenge. But one of the key reasons is the volume of the data that these satellites are collecting. So each of these LEO satellites can collect about a terabyte of data every day. Oops, I'm sorry. Yeah, so each of these satellites can collect about 1 terabyte of data per day. So as a constellation, they collect hundreds of terabytes if you have a constellation of hundreds of satellites, and getting this data to Earth is challenging. And this is even more challenging because of the orbital dynamics of these satellites. So remember, I said that these satellites have very fast orbits, and they can orbit around the Earth, around the poles, in about 90 minutes. So if you're a ground station observer on the Earth, you will see the satellite go from horizon to horizon in less than 10 minutes. So you're getting this terabytes of data from these satellites, and your receivers on Earth see these fast-moving objects that are only in contact for just 10 minutes. And as you can imagine, this is a challenging like data downloading problem because you have to download like this high volume of data in a small context that you have with these satellites. So at a high level, this is the entire data downloading pipeline. So you have satellites that transmit images to the ground stations, and then ground stations that transmit these images to the cloud, at which point this image is processed and sent to the consumer. And there are latencies at each of these hops. So at the first hop, you have the satellite to GS or the ground station, you have ground station to cloud, and then even at the cloud, you have to generate insights from them and send them to the consumer, and all of that incurs high latency. So in the first part of this talk, I'm going to focus on this link, which is the satellite to ground station link. And I'll broadly cover the work that we've already published in SIGCOMM 2021. This is a paper called Ed2D2, along with my students Jay and my mentor at Microsoft, Ranveer Chandra. So today, the way these ground stations operate is that you deploy a small number of very large and very complex multi-million-dollar ground stations. These are heavy investments. They look like the big antennas that you see on the right. You would deploy like 4 to 5 massive ground stations, and you would want to locate them close to the poles because you get more revisits, but not always, depending on some other constraints. The problem with this current model is that you experience large latency because you're going around the Earth and waiting for ground stations to come in contact with you. Your latency can be on the order of hours. And as I said, for applications that require low latencies, this is not really feasible. The second challenge is that scaling in this kind of context is capital intensive. So it is okay if you have few satellites and a couple of ground stations, but as you go to more and more satellite deployments, the scaling becomes challenging because you like make heavy investments, get licensing, get land, like deploy all of this. It is quite challenging. And finally, failures are weather disruptive. So imagine that you are a satellite that's waited for like 3 hours to get to a ground station, but suddenly you see the weather is cloudy, your link does not work, or if there is a hardware failure, so you have to wait for another like 3 or 4 hours before you get an opportunity to come in contact with the ground station. And just to give you a sense of this, typically you would get about like 4 to 5 good contacts with each ground station in one day. Actually, like it may even be fewer. And then depending on the number of satellites, there's contention and all of that. So our idea is to move to a new model of ground station deployment, where instead of deploying these like capital intensive huge ground stations, you have a distributed hybrid ground station, which consists of like small, low cost ground stations deployed on rooftops, backyards, closer to data centers, wherever you can actually deploy these small dishes, and then distribute them geographically. And then we use software abstractions to make all of these distributed units behave like a unified single ground stations that provide a continuous connectivity abstraction to the satellites. And one key feature of our idea is that a lot of these units are receive only. So as you would have noticed by now, that there is a lot of downlink traffic from these Earth observation satellites, but not as much uplink traffic. And that makes sense, right? Because the uplink traffic is just for telemetry control, which is small amounts of messages. So the uplink does not need to be prevalent on all of these satellites. And it makes a lot of the hardware design as well as licensing easier because you're not transmitting any data, you're just receiving data. Okay, so this is how it looks like visually. So today we have like few of these complex, heavy ground stations. But instead, what we want to move to is a world where we have distributed ground station capacity across the world, and they provide a unified abstraction of continuous connectivity to these satellites. And this kind of design has several benefits. So first of all, this is fault tolerant. So even if some of these units go down, you would still be fine because you have other ground stations to take over. And one way to think of this is think of this as a cloud versus is the supercomputer versus data center based cloud. So imagine in a supercomputer world, you have these like investment heavy large computers in the past, but now you move to this world where you're like kind of commodity computers stacked together, provide you the same kind of abstractions, and they're more fault tolerant because if some of these units go down, that's fine. We've built systems that take that into account. And then there is a lower latency because you can almost always get in touch with the ground station if you want to download your images. And finally, as I said, our ground stations are hybrid. Not every ground station needs to transmit data. And this is actually interesting because, like Amazon tried to launch a ground station service, but they had to deal with a lot of issues before they could actually transmit data. And they suffered like kind of long delays because of licensing for transmit capabilities. And for a long time, they had to deploy receive-only ground stations just because of the licensing delay. So it makes sense to have a lot of receive-only stations as opposed to having like every ground station be transmit capable. So the question is, can a network of these tiny ground stations outperform the capital-heavy huge ground stations, right? Like what can we do to make that happen? So there's several like technical challenges that we have to solve for this, and I'll talk about some of them today. So the first challenge is rate adaptation without feedback. So typically in wireless systems, you have to decide like what data rate you want to transmit at. So for example, when you have a phone talking to your access point, it needs to figure out like what's the right data rate, because if you transmit at a high data rate and your link cannot support it, then you end up suffering from packet loss, which is bad. If you transmit from too low of a data rate, then you are spending too much time on the link, which is also bad for the system and bad for you because you don't have to wait that long. So what is the optimal data rate? That will not lead to a lot of packet losses, but it's also good enough for you. So and this kind of problem is important in the satellite context as well, because the link quality varies by a lot. And I'll give you some examples of this. So link quality typically varies by 10 to 20 dB in one contact between the satellite and the ground station. It depends on the elevation of the satellite, the weather, the equipment. You can actually think of this like the sun, right? So if sun goes from like morning to noon to evening, you can see like varying intensity of heat. And this is very similar to what happens for the satellite, except in a span of 10 minutes. So in a span of 10 minutes, it goes from horizon to horizon. And what that means is that when you're at the closer to the horizon, your link is very low. When you're up above in right overhead, your link starts getting better. But in our case, unlike your phone and the access point, we do not have any feedback. So the way your phone would decide what data to transmit at is by talking to the access point and be like, hey, can you tell me if this rate works? And the access point will be like, hey, okay, this works. Or it can be like, hey, I lost the packet. Clearly, I did not see anything. That rate does not work. But in our case, we do not have that. Our ground stations cannot give feedback because a lot of them are receive only, but the satellite has to still find the optimal data rate to transmit at. So yeah, so how can we do rate adaptation without any feedback from the ground station, or at least the receive only ones, which forms a large fraction of this distributed ground station architecture that I talked about? And again, to add more color to this problem, I'm going to show you this graph, which shows the link quality of an X-band ground station. And on the x-axis is time in seconds. On the y-axis is the SNR in dB. And this is from like a NOAA satellite transmitting to a ground station in the X-band. And we measured the SNR over time. And as you can see that in the beginning of this link, the link quality improves. And at the end, like the link quality goes down, which is expected, like similar to what we thought about the sun. But at the center, you see there's this like dip, which is kind of unexpected because you expect the link to be the best at noon, right? But that doesn't necessarily happen here. And our hypothesis is that a lot of that is because of the surroundings of the environment, because you may have reflectors close to a ground station. You have like reflectors on the satellites. They cause this effect called multipath, which leads to these kind of like non-obvious patterns in this link quality. So then we compared this on a different day for the same exact satellite ground station pair for the same kind of orbital path. And we see that the link has dipped in quality by a little bit because of like slightly cloudy weather. So there is the impact of weather and the impact of where the satellite is. And there's an impact of like multipath of the reflectors around the satellite. So in total, there's like 3 different kind of losses that need to estimate. You need to estimate what is the propagation loss, that is, if the longer you travel, the weaker your signal is. What's the weather-related loss, which is that if the weather gets cloudy, you'll get weaker signals. And if you have like things close to a device, both the transmitter and the receiver, it can cause multipath. And if we can estimate all of them, if we can predict the distance using, say, orbital parameters, we can estimate the weather-related loss using weather forecasts, and we can train a machine learning model for multipath and hardware losses. We can combine that and identify what is the optimal data rate to transmit the signal at. So if I know the link quality exactly, then I can use that to estimate the data rate. So we have a machine learning model that can predict this link quality, and this is how it works. So it has actually an ensemble model, which means it uses a random forest and a neural network to make predictions, and combines these predictions to find the optimal SNR, which is the data rate or the link quality, and then you use that to infer the data rate. And by doing that, we can predict the data rate and transmit data on that. So the second challenge is around scheduling, but I'm going to actually skip this because I'll talk more about this later in a more detailed fashion. And I'll actually really quickly move to an evaluation of this and the overall architecture, how it operates. So at a high level, this is how the system operates. So a transmit capable station will upload a plant to the satellite. And as the satellite moves around the globe, whenever it comes in contact with the ground station, it will use the plan, which contains the ideal data to transmit at and transmit this data. And the next time it goes to a new ground station, it will transmit its data, and all of this data can be collated in the cloud or at the backend. So for evaluating the system, we've looked at multiple real-world measurements at different ground stations and satellites. So at 5 different ground stations, 4 different satellites like GPSS, SNPP, APO, and Terra. And we performed measurements across 1 month in 2020. These ground stations kind of cover like half of the Earth's horizontal and vertical span, or the longitudinal and latitudinal span. So they're kind of like geographically diverse. So one result that I wanted to show you is that how accurate can this link prediction be for you to use this either in like, actually, you can also use this for communication satellites as well as Earth observation satellites. So this is the link prediction accuracy, or the x-axis is SNR error in dB. So the lower the error, the better, and the y-axis is the CDF. So as you can see, with our model, which is the DJS model, the error is way lower than even like standard ITU models, which do not account for these hardware-specific changes or like small temporal changes because of, say, the weather variations. And actually, in terms of predicting the optimal data rate, we make about 6% error as opposed to like 41% error that the ITU models make. So we also did a large-scale emulation for this. So we don't have, like, of course, like as big a network yet, but for large-scale emulation, we have 259 satellites and 173 ground stations from the SAT-NOX framework, and we emulated the same kind of links that we saw in our real data set on this link with 100 GB of data transfer per day, 26 terabytes total, with 5 ground stations as a baseline. So the baseline is 5 big ground stations, each of which has 10x capacity. And then we have 173 like kind of tiny ground stations, which is what the SAT-NOX framework provides us for the distributed ground station. And the key insight from here is that distributed ground station can actually reduce latency from hour to minutes by using this this distributed architecture. So yeah, so I'll quickly jump to the next part of the talk, where I wanted to talk about scheduling as well as latencies from the ground station to the cloud link. And these are some early results from an upcoming paper at MobiCom 2023, where my students like Bill Tao and Malhiya Masood will present this work. Okay, so the key idea here is that that there is this thing called uneven queuing effect, and I'll explain what that is. That leads to large latencies at the ground station in the ground station satellite link. And this is the reason. So imagine that a satellite travels all across the world, comes around to a ground station, and it has a bunch of these images. It will, of course, like try to transmit as many of these images as possible to the ground station in this contact, and let's say it's able to transmit all of them to this ground station. But if there's a next ground station which is close by, when it gets to it, it has way fewer images because it only collected like a small number of images in the middle, and it can transmit only this small number of images to this ground station, to the second ground station. So what this leads to is that some of these ground stations have big queues, and some of these ground stations have smaller queues. And in networking, you know that bigger queues always leads to larger delays, and that can be a problem. What makes the situation worse is how these satellites are organized. So this is these are the Planet Dove satellites. So this is a constellation of about 200 satellites. If you look at the Planet Dove satellites, how they're organized in orbits, they operate in these 2 orbits. And it's essentially like a satellite train, like following each one after the other. So imagine that instead of one satellite in the previous example, you had a satellite train going over this and keep experiencing the same effect that we saw earlier. So what you would have is that a really large queue built at the first ground station and kind of a tiny queue at the second ground station. And if you keep doing this, any satellite that encounters the first ground station or transmits a lot of this data to the first ground station will see a large delay in getting that data to the cloud. On the other hand, the second ground station will see a lot quicker transfer of data. So how do you solve this problem? So we define this paradigm called withhold scheduling, where you don't take the greedy approach. And what I mean by the greedy approach is that you transmit as much as data as possible in each of these satellite ground station contacts, but you use the storage on the satellite to store some data for the future. Okay, so the idea is that when it comes to the first ground station, instead of transmitting all of its data, it keeps some of its data for the future. And by the time it comes to this next ground station, it has collected some additional images, and it can transmit the data that it stored and the additional images to the second ground station to equalize queues. So this is kind of a complicated question, because how do we make these withholding decisions? What is optimal? It depends on the orbital patterns. It depends on so many different characteristics of the network. So clearly, like making these decisions is challenging. I'll not talk a lot about how we actually make these decisions, but give you like a brief overview, and more details can be found in the upcoming MobiCon paper. So the idea is to use what we call time extended graphs, so expanded graphs. So if you look at one instance of time, you can frame this satellite scheduling problem as this graph on the left, which has a satellite connecting to a ground station through these links that are temporal, that vary over time. Now, you can extend this graph over time. At a different instances of time, you will see that these graphs make different links. But we also create these temporal links from a satellite to itself in the future, and these links keep extending, and same for the ground station for itself in the future. It makes a link to itself in like different instances in the future. And by doing that, we can enable satellites to save some data in the storage in the hope that they will find like a better connection in the future. And similarly, like ground stations can store some data in on themselves in the future. And this is this is basically kind of an interesting trend now that satellites and ground stations both have like storage capabilities and compute capabilities. So we can leverage these kind of intelligent decisions to store data for future contacts. And if you just squish this graph, this is what it looks like. There's an imaginary source generating this data, and all of these ground stations are uploading this data to the cloud. So essentially, at some level, this becomes very close to a max flow problem, and we'll present like more details in this paper. And finally, like just to conclude this talk, I want to briefly mention some like ongoing work on leveraging compute on the satellites themselves. So as I said, like right now, the pipeline is that you get data from the satellites to the ground stations to the cloud, then you generate insights. All of this process incurs a lot of delay. But increasingly, satellites have compute and storage capabilities. So can we use the storage and compute capabilities to flag important images sooner so that they are prioritized through the network? So imagine that I find a California forest fire being detected on the satellite itself. Can we prioritize the scheduling of that image through this network so that I can get this to the consumer as fast as possible? And there's like many interesting questions here. For example, how do you schedule compute? What compute happens at what location? Like what compute is being done on the satellite? What compute is being done on the ground station? What compute is being done on the cloud? And this is like another interesting question that some of us are looking at. So I hope I've given you like a really rapid overview of the different challenges in getting near real-time insights from Earth imagery satellites, and I'm happy to take questions. Thank you.
Thanks, Deepak. It was a great talk, and we have some great questions as well. So the first question is from Nishant Shastri. Which weather is important? Is it close to ground or higher up in the atmosphere? Nishant guesses it's the former, but it would be good to hear from you.
Yeah, thanks, Nishant. So it is the former. It is the one that's closer to the ground. So mostly, I think it's about clouds and rain. So if there is like a lot of clouds, a lot of rains, they can definitely block a signal by quite a lot. And that's what we try to model.
All right. So the next question is from Tony Lee. ISPs are having no problems getting small ground stations to have some transmit bandwidth. So why can't you make use of a similar solution?
Yeah, so I think that's an interesting question, and there are like many like answers to this. But one part of the answer is that ISPs typically is just around the licensing paradigms. Like the way ISPs get licensed is very different from licensing for these like ground stations for Earth observation satellites. But also there's like different other solutions being explored. For example, like satellite links, like the inter-satellite links for speeding up some of this access. And in general, I think even with the transmit, like small amounts of transmit bandwidth available at these ground stations, the idea of having a distributed ground station that behaves like a fabric as opposed to these like individual segregated ground stations is interesting and relevant.
Cool. So we'll take another question, the last one. It's on the queuing challenge, and it's from Rohit Reddy Venam. We know the available ground station locations and satellites maneuver. Can't we take these known parameters and schedule accordingly?
Yeah, so we do take these known parameters into account when we are doing the scheduling with Umbra. Yes, we do, and we should, yeah.
All right. So thanks, Deepak. Thanks once again. Thanks for joining and for giving this great talk.